Hi everyone! Did you know that it's possible to control speech enhancement by brain signals? The answer is yes, and we can use it for hearing aid applications. I'm Aroudi and we'll talk about cognitive-driven convolutional beamforming using EEG-based auditory attention decoding.
This work was done in collaboration between NTT and the University of Oldenburg during an internship and visiting at NTT. Generally speaking, consider an acoustic scenario with multiple speakers. There are many speech enhancement algorithms available to reduce noise. But in a multi-speaker scenario, which speaker is the target to be enhanced? Correctly identifying the targeted speaker is crucial for improving speech intelligibility. For identifying the targeted speaker, we use EEG signals and hearing aid microphone signals to decode the listener's attention. Or let's say we perform auditory attention decoding or AAD. For AAD, we use a least squares based method proposed by O'Sullivan in 2014. This method requires appropriate reference signals for decoding. But in real-world conditions, only the microphone signals consisting of a mixture of speakers, including reverberation and background noise, are available. So for AAD, appropriate reference signals from microphone signals need to be generated. And more importantly, we use AAD to control speech enhancement. And that's why we call it cognitive-driven speech enhancement. But currently available systems are not able to suppress reverberation. What is reverberation? In a reverberant environment, the speech signals of speakers are directly arriving at the ears of the listener as shown by the black arrow in the figure, but also their acoustic reflections against surfaces and objects are arriving at the ears of the listener as shown by the gray and red arrows. The reflections arrive early at the ears in order of tens of milliseconds shown by the gray arrow are early reverberation which can be beneficial for speech intelligibility. However, late reverberation or the red arrow occurs later and is known to have a negative effect on speech quality and intelligibility. This brings me to our project goal. The goal is to generate appropriate reference signals from hearing aid microphone signals. Then we do AAD to identify the targeted speaker. The other main goal is to enhance the targeted speaker and jointly suppress reverberation, the interfering speaker, and ambient noise. And for that, we use a recently proposed convolutional beamformer. Also, we note that suppressing the interfering speaker is desired to improve speech intelligibility, but keeping the interfering speaker audible is also important to allow the listener to switch between speakers. That's why our next goal is to control the suppression level of the interfering speaker to keep it audible. And for that, we extend the convolutional beamformer to include a linear constraint on the interference suppression. First, let's see how AAD works. The least squares based AAD method consists of two steps, a training step and a decoding step. For the training step, let's consider an acoustic scenario with two competing speakers while EEG responses of a listener to these stimuli are recorded. Before the experiment, the listener is instructed to attend to which speaker. After EEG recording, to identify to which speaker the listener was attending to, a spatiotemporal filter is applied to EEG recordings. This filter aims to reconstruct the envelope of attendant speech signal from EEG recordings. This filter is obtained by minimizing the least squares error between the envelope of the attendant speaker and the reconstructed envelope. And of course, we do regularization by this term to avoid overfitting. For the decoding step, the original AD method required clean speech signals of both speakers, shown here by Ref1 and Ref2. The envelopes of these speech signals are extracted and then correlated with the reconstructed envelope. If the correlation for the first speaker is larger than the second speaker, then we would say the first speaker is the attendant speaker and the second speaker is the unattended speaker. Please note that here, it's assumed the clean speech signal of both speakers as reference signals are available, which is unrealistic in real-world conditions. In recent work, it was proposed to use conventional beamformers to generate reference signals. In this work, we investigate using recently proposed convolutional beamformers. Okay, with this introduction on AD, let's see how our cognitive-driven convolutional beamforming works. Here we have two competing speakers, a listener equipped with EEG electrodes, and hearing aid microphones. We first estimate the mask of both speakers from microphone signals using a speaker-independent speech separation neural network. Then beamforming comes in to generate reference signals by enhancing the speech signal of each speaker based on the estimated mask. We use either conventional or convolutional beamformers. The AED method then selects one of the reference signals as the enhanced attendant speech signal. Okay, let's see how a conventional beamformer works and what is its difference with a convolutional beamformer. A conventional minimum power distortionless response, or MPDR beamformer, aims at suppressing noise while preserving the target speaker. So it means that it is designed only for beamforming. As it's shown here, it takes a stack vector of all microphone signals as input, and then beamformer output is generated by linearly filtering and summing the microphone signal using the beamformer coefficient, or W. Here we have the beamformer optimization problem, where Ry is the covariance matrix of the current frame of the microphone signals, and this terms ensures the target speaker is preserved. And A here is the reverberant relative transfer function, or RTF vector, which relates the acoustic transfer functions between the target speaker and one of hearing aid microphones. The RTF needs to be estimated, which is actually not a trivial task in practice. And now let's see the difference between this beamformer and the convolutional version. A convolutional weighted MPDR, or WMPDR beamformer performs jointly dereverberation and beamforming. As it's shown here, it does dereverberation, so here we have dereverberated signals, and then beamforming comes in. The output signal of this convolutional beamformer can be shown as this equation, where first dereverberation comes in and then beamforming. And this entire equation can be squeezed using this notation, where W bar denotes the stack vector of the reverberation filter coefficients and beamformer coefficients, and Y bar denotes the stack vector of past and current frames of microphone signals. Please note that the difference with respect to this conventional beamformer is that here W consists of beamformer coefficients. However, for the convolutional beamformer, W bar here consists of the reverberation filter coefficients and beamformer coefficients. What about the optimization problem of the convolutional beamformer? Actually, the optimization problems of the conventional and the convolutional beamformer are similar, except that here a covariance matrix of the stack vector of the past and current frames is used. Also here, a relative early transfer function, or RETF, is used, which is important for the reverberation and needs to be estimated. Okay, now let's zoom out a bit. In general, these beamformers can strongly suppress the interfering speaker, which is good for improving speech intelligibility, but it may deprive the listener to switch attention between the speakers. Because when the interfering speaker is suppressed, not easy anymore to attend the interfering speaker, right? And this actually motivates to use an LCMP beamformer to take care of interfering speaker suppression. The conventional LCMP beamformer adds an interference suppression constraint to the MPDR optimization problem, and this allows to control the suppression of the interfering speaker. So this term here allows to control the suppression level of the interfering speaker with parameter delta, and B here is the RTF vector of the interfering speaker, which needs to be estimated. However, the conventional LCMP doesn't perform the reverberation. Therefore, one of our novel contributions is to extend the convolutional WMPDR beamformer to include a linear constraint on the interference suppression as we see it here. So this beamformer aims at jointly beamforming, dereverberation, and also control interference suppression. All of these beamformers require either RTF or RETF. To estimate these parameters, we use the covariance whitening method, and the estimation is performed based on the masks of the speakers, which are estimated using a speaker-independent speech separation neural network. Let's move to experimental evaluation. For experiments, we considered two audio stories uttered by two male speakers as acoustic stimuli. We considered three acoustic conditions for EEG recordings, and evaluating our algorithm consisting of noisy, reverberant, and reverberant noisy conditions. We split EEG recordings to trials, each of them 30 seconds, and then we made AD decision per each trial. For AD, we considered Oracle AD, which means the best beamformer output was selected as the attendance speed signal, or X hat A here. We also considered estimated AD, which means the attendance speed signal is determined based on the highest correlation coefficients. For mask estimation, we considered Oracle ideal ratio masks, meaning that we computed masks from perfectly separated speed signal. It will be later shown by OMask. Also, we estimated masks using neural network with 3 BLSTM layers. For beamforming, we considered WMPDR and WLCMP convolutional beamformers. We also considered conventional LCMP and MPDR beamformers. And our baseline is a system consisting of MVDR and LCMV beamformers, which are steered based on the direction of arrivals or DOAs of speakers. This work has been recently published. Let's see the difference between the baseline system and our proposed system. In baseline system, conventional MVDR and LCMV beamformers are used, which are steered based on the DOAs of both speakers. However, in our proposed system, conventional and convolutional beamformers are used, which are steered based on the mask of both speakers, estimated using a source separation neural network. Let's move to experimental results. Let's first have a look at the speech enhancement performance of the convolutional MPDR and conventional MPDR. On y-axis, we have frequency-weighted segmental SNR improvement averaged over all considered acoustic conditions, and on the x-axis, we have beamformers. The blue bars show results using Oracle AD, and the red bars show results using estimated AD. We see the convolutional beamformer yields the largest improvement for both Oracle and estimated masks, as well as for both Oracle and estimated AD compared to the conventional and baseline beamformers, thanks to jointly the reverberation and beamforming of convolutional beamformer. Also, comparing blue and red bars shows that AD errors degrade improvement for all beamformers because the targeted speaker is wrongly identified and therefore suppressed. And now let's look at the speech enhancement performance of the convolutional LCMP and the conventional LCMP. We see the convolutional LCMP beamformer yields the largest improvement for both Oracle and estimated mask, as well as for both Oracle and estimated AD. Okay, up to now the results show that the convolutional MPDR and LCMP beamformers yields the largest improvement. And now let's compare the performance of these convolutional beamformers itself. We see that the convolutional CMP yields a lower improvement compared to the convolutional MPDR. But it is expected, right? Because we explicitly aim at maintaining some level of the interference speaker to make it audible or to allow the listener to switch attention between the speakers. So in summary, most cognitive-driven speech enhancement algorithms are not able to suppress reverberation. We proposed a cognitive-driven convolutional beamforming system, which allows to enhance attendance speaker and jointly suppress reverberation, the interfering speaker, and noise. The proposed system outperforms the system using conventional beamformers. Also, we proposed an LCMV convolutional beamformer, which is able to both control the interfering speaker suppression as well as yield a considerable improvement. And of course, there are rooms for improvement. For example, better estimation of RTFs and masks of speakers is required. Also, a better AD method can help system performance improvement. Here is the references used for the slides, and thanks for your auditory attention. Looking forward to your questions.